wasn't possible. I'd also like to carry forward and support a comment that Lisa made, and that was BLM trying to get access for people, technology purveyors, to try and get them tried out, evaluated, looked at. And I want to give tremendous thanks to both them and EPA for allowing us to do what we've done here. And we came at it from the approach of looking for a steady stream that we could actually run for periods instead of just beakers and 5-gallon buckets and totes. And that's kind of where we're headed to get our technology where we are. There's two technologies that we've coupled together. One is the advanced neutralization, or AN, and that uses electricity to treat water. And then we've used the MBT technology to tie up metals so they're stable long-term in solids that are formed. Again, I'm just going to touch on the lime real quick. Lime has certain problems in that there's certain metals that come out at different pHs as hydroxides. Hydroxides are stable, but when the pH changes, hydroxides are neutralized, and therefore the metals are released. Part of the technology we ran into was pulling the metals out, and we found that we needed to get the acidity taken care of first. So this just shows a time study with pH in our first stage of what we do in the AN technology. First, after bucket tests and beaker tests, we developed a 1 to 5 gallon a minute system. And a little story that was made by a bong maker in Oregon. It's the only way we could really see the layering in small volume. We had different layers to pull out the different layers of sedimentation. We use electricity. We do have electrocoagulation as part of it. That helps start the seed to get the coagulation. But the other parts of it involve oxidation reduction, and we have inert, sacrificial, non-sacrificial electrodes that are dimensionally stable that create reactive surfaces. And we also have a catalyst, and that causes the dissolved metals to start to precipitate as oxides at a low pH, under 7. So our ideal operating pH is between 6.5 and 7. And then this is our upscale unit, up to 20 gallons a minute. We brought this out here last year in October, and we ran it about 7 different trials, and the final one was at about 10 gallons a minute, and that was one of the units. And that's what most of this data is about today. We started our work on this before the Gold King incident. This is at Bunker Hill Mine, and we treated Kellogg Tunnel with our lab unit out there. And that was when we first started working with it. We then came out here after the incident, and we pulled water from Mogul. And you can see where our solids are in our system were starting to coagulate. And then this is some of our clarified effluent through the bong. Oops, we looked at solid settling, and that's over time in our columns. We took treated material off the system and ran it basically and did a column study to see what our settling times were. We also thought, well, we've got something. We're not generating a lot of solids. Let's see what we're competing against traditional technology, which is lime. So this is done back before the lime system was up and running here. This is on Mogul water, and you can see our data here, our treated effluent, and this is lime at 2 different pHs. Again, we tried to get the right pH to get the metals, and you can see that the red ones didn't quite make it, the blue did, and the white ones were good. And then you also look at the solids that were generated. This is the lime solids, and that's how much, at the same time settling, that's the same volume of solids that came out of the AN technology. From that, we actually got access to Gold King mine water, and we came up here and pulled samples in the spring of 2016 and ran studies. Took water back home, and we actually ran some down in Durango and ran some studies there. And some of that data, again, here's your data, it's going to be tight to see, but we ran through a series of different tests. This is our untreated levels. I know zinc was mentioned, total and dissolved, and in our somewhat optimized, we were less than 0.02 milligrams per liter. The issue that we had at that time was manganese, and that's where we started working a little more with the oxidation reduction potential, ability to change it in the technology. So we're now able to get manganese out. We also get arsenic and selenium out because they are kind of fight each other for electrons. And then in October, we came out and did the study at American Tunnel site in Gladstone. We actually took water from the Gold King mine out of their vault right here, and we ran it through a series of tests. And intent was to run it for a period of time that allow us to go about 10 gallons a minute, where we could work with some operating variables. And we did, and it took us a while, longer than we thought, but we were able to. And this is just some of the samples we pulled off at different regimes of running and showing the inside. This is one of the components in our system. Not totally related to what Lisa and Kirsten were talking about, but you have a media, you get barrelcrete, you get all kinds of sedimentation. This is a tumbler for our reactive site media. And what that is it's triaxial spinning motion. It spins and it causes the media to tumble, and it prevents any buildup and scaling on it. We also need the media for a reactive surface for part of our reactions. Before we came to the study, trial, we had to make sure we were going to work because we only had a short time. We did some work with Summitville, American Tunnel, and Gold King before we came out again. This is one of our mixing units, and this is part of our system getting put together before we came out. Current system in Gladstone, that's where we set up and ran. We had our water treatment system in here. We ran about 10 gallons a minute through that. We actually pushed 20 through it at one time just to see if mechanically we could get through it. We didn't try and treat it. And then we also treated our solids in this area. Again, that's the Gold King, and the upfront influent ponds where we set up. This is looking down at one of our reaction chambers. Again, some of the water that came off, and that was a sample of gravel we did of our final run, which actually went in for the testing. And here's our data. We've got some initial data that came from EPA BLM. Pointer here. Two different time frames. That's the raw influent. That's lime treated effluent. These are some raw influents that we pulled or had pulled. And then these are our different runs. And this is the one that we not quite optimized, but pretty good. And then we ran a QA/QC field blank. It was a blind blank that went to the lab. So that's a water treatment component of it. As I mentioned, we didn't have a whole lot of solids. We don't generate a lot of solids, and we didn't really run it long enough, even at 10, 12 gallons a minute, to get the solids we needed to do the treatment on. We don't get very many solids. So we also then looked at, oops, went the wrong way. But one more piece. The technology, what we did do with the study also was to generate enough data so that we can figure out how to put these units, our treatment system, inside shipping containers or Connex boxes so they can be outside in the weather, secure, protected from the weather, or better yet, put inside a tunnel and add it. And this is a 50-gallon-a-minute clarifier that we built for a pre-treatment high-density sludge system that went up to a large zinc mine in northern Alaska. And this is in a shipping container. That one had a lot of filters on it, but that's one of the clarifiers we would use for our technology. So we then went to the lime solids. And we knew that there was an issue. We had talked with EPA and BLM, what were we going to do with the solids? So we were looking at ways to see if we had something that would work. And so we got some lime treatment solids, and we used, the MBT technology. Instead of forming hydroxides, we form other mixed minerals without going into the details of them. If you use our geologists or mineralogists, you know which metal forms are very stable. And we form multiple. So I call it, instead of a metal hydroxide, we're calling it a metal MBT. So this is a composite of all the potential solubility products of the minerals that we form with those metals. And if you compare it to the metal hydroxide, again, you look at the very low negative exponent, that means it's very, very insoluble. The higher the exponent, the higher the number, the more soluble it is. So that just compares the MBT metal compounds versus the metallic hydroxide compounds. And this is where we're treating our solids with our mixer. Then we took the MBT treated solids and we wanted to look at what we could do besides just TCLP and SPLP testing. We thought, well, if they're looking at a place to manage and store treated materials at mine sites anywhere, you got to be able to withstand acidity, prolonged periods of acidity. So what we did is we collected water from the Cement Creek at a pH about 4, a little under, and American Tunnel. And then we took our untreated lime solids, and these are the total metals that were in there, and we treated those solids, and then we used, in separate tests, the fluid from each of those sources as the extractant. So instead of using a TCLP fluid, we used the Cement Creek water or the American Tunnel. And then instead of just doing it once, we did it 10 sequential times. So we took the treated material, leached it once, took that material, analyzed the fluid for the metals, took that solids to the next step, new fluid, same source, did it again. We did that 10 sequential times and looked at the metal concentrations in each of those extracts. And this is the American Tunnel. And again, here we took the American Tunnel waters are extracted. We did untreated lime solids, and we also did the MBT treated solids. And again, I showed some of these yesterday, but here's an example of aluminum. So this 4.61 on the blue line here is what the total aluminum was in the fluid. 3 minutes left. Till 20 or 15? Okay. Okay, so that is, for every time we did an extraction of the 10, we had 4.61 milligrams per liter of aluminum in that fluid for each one. So that's the starting fluid that went into that material. The broken line here is untreated lime solids, so that went through that 10 extraction. And then the green line is our treated MBT material. Basically, we took this material and treated it with the MBT. And what you're seeing is that these treated materials at the bottom and through the lime solids actually remain stable, but it also pulled the metals out of the fluid itself that it was applied to. And that continued on, at least for aluminum, until about the 6th extraction. And the lime solids can no longer pull metals out of it anymore. It started to break out and leach. The MBT went out 10 serial extractions. A little background on the MBT technology. It's an EPA method that came out a long time ago. And the idea was to replicate a synthetic approach to basically 100 years of exposure to acid fluids. And then with 10 of them, it's kind of a model to look at what 1,000-year exposure would be. This is cobalt. Same concepts here, untreated. That's the cobalt that was in the American Tunnel water, and that's what came out in the MBT treated. There's copper. Manganese. There's manganese, and that's the untreated. That's the manganese that's in the American Tunnel. And then again, the treated material, the treated lime solids actually pulled the manganese out of the water, which is the American Tunnel. And that's what was after 10 sequential extractions. Nickel, and then zinc. So that's American Tunnel. I just pulled some of them, and because of time constraints, we did the same study, but we used Cement Creek water. And that's where it came from. Again, here's cadmium. Again, cadmium was quite low in the Cement Creek water. Green. Sorry about this. I'll just go to zinc. It's the same pattern, so. Again, zinc in the water from Cement Creek. This is what came out of the untreated lime solids. And this is what came out of the MBT treated lime solids. So what that told me, and other people have looked at the data that I work with, and folks, is that if you treat an MBT, or treat a solid that's got metals with the MBT, it is able to be put into an acidic fluid and retain its stability. In other words, the metals won't leach from it. The last thing we did, we took a lime solid and Kittimac Tailings and did a quick treatability on that at different ratios. And this is the data we came up with. And I'm going to go through this quickly because I've got a little more detail. We didn't know what a treatment objective criteria was. What is treatment? What's success? And so we took the data and we then, this is a table I'll go through quickly. I didn't know, they talked about numeric standards, water quality standards, table value standards, and I didn't know which one really applied because I'm from Washington. I don't understand all the state regs here, but I do understand EPA. So we put a table together and we looked at what the limits would be as under water quality. We then compared, and what we did then is we took all these standards and made a blend out of it so we could make it easy. So we took the least and the most and the mid-level and we created three threshold levels. This is based on total metals in water. And we thought, well, if we can meet any of those criteria in there with our metals and our leachate, then we're doing pretty good. So that's what we did. This is the least stringent numeric range threshold that we had. And we looked at the leachable metals that came out in TCLP extract of untreated lime solids, untreated Kittimac tailings, and then treated lime solids and Kittimac tailings with lime and with MBT, and at different ratios, 1 to 1, 1 to 2, and 1 to 5. Basically, the green is the limit. The red is where there's a problem. And blue shows that it's basically a pass all the way across. And we didn't optimize here. We took the same dose that we used from our field trial. We didn't know if it was right or wrong. We didn't know what to shoot for. So all the treatment we did here was we just tried it, see where we end up with. And we didn't do too bad. We got a couple here that if we optimize, we can get out the manganese. We didn't know where we were on it. So that's under the least, that's the moderately. And then here's the most stringent. And remember, these are all total metals versus dissolved. So we're not looking at any dissolved fraction here in the data.
We wanted to leave 2 minutes for questions. And so if you wanted to give your sort of 30-second wrap up or ask for questions from the audience.
I can take them after here. I've got data I can give to people, email it to them if they'd like it. They're offering a free treatability study, although you have to pay for your lab work if anybody's interested. Take some forms, send samples to us. 3 points I'd like to make is acid mine drainage. There are treatment alternatives to lime that are less costly. There are leachable metal substances defined by CERCLA that can be tied up long-term so they don't leach for long-term placement on site or in a mine. And there are contractors out there that will take a lump sum per dollar bid using a technology, and they'll take the risk of payment or non-payment. Just need to know what the performance criteria are. Lisa. Well, for the water, 5-gallon bucket works. That'd be a lower one, but I was thinking more on the sediment side for the solids. 5-gallon bucket works, but if you really want to get a quick 500 grams in a Ziploc bag. Yes. Good question. Right here. I'm sorry, I skipped over that too quick. So that's lime solids. That's Kittimac tailings, a little bit of water, so we can get a little better mixing during the treatment. And this is treated material after about 10, 15 minutes. It's just basically like what it was. What changes its consistency is what's added to it. It can be made compactable, so you can get a suitable fill material out of it. And I saw, you might have seen the slide, I had the dust, there's the dust issue of metals, and that can be corrected with certain geotechnical properties that can be enhanced with it. Yes? For the water or for the solids? I need to know what metals are in it. Manganese can be a bugger. Some of the other divalents. And again, there's a huge range here because of how many metals or what's your level you can accept or are you able to tolerate within your extract or your leachables. But it's probably in the reagent cost without mixing, anywhere from the $10 to $50 a waste ton.
Last question. Joy.
The ratios that we used here were under 10%, but that include water weight too. We're not a hydration reaction. We're more of a dehydration. It's not pozzolanic, so water that's added is used for lubricating and mixing and not to hydrate into as a hydroxide into the, or hydrate into it. So if you add 10% weight, you're probably getting a 5-6% mass increase.
Awesome, thank you.
Thank
Clearly,
you.
it's a great technology.